All right, hey, you finished the first half of Calc 1. Can you believe it? Let's do a quick recap of the first half of Calculus 1. Yeah, it can be recapped with our little slogan, right? When I say derivative, you say slope. Derivative. Slope. All right, so the first half of the year is derivatives. Congratulations. So what do you think the second half of the year is? Oh, you think it's the topic that we kind of previewed a little bit? Well, you're right. It's called an antiderivative. Yes, the second half of the year we'll be focusing on trying to do derivatives backwards. So what's the backwards of slope? Well, it doesn't really quite work that way. Actually, when I say antiderivative, you say area. It doesn't really roll off the tongue as nicely, but it is true. You see, these things we're finding called the antiderivative, well, eventually they will help us to determine area. Often we call it the area under a curve, but we're not quite there yet. Let's take a look at the train problem. Sure, you can jot this down if you want to. As you jot it down, or if you're just reading it, you might be wondering, what is the catch? Well, there is no catch. So let's consider the train problem a train that goes 75 miles an hour from 7 to 9 p.m. What's the total distance traveled? Is this just a simple distance equals rate times time? It sure is. We've got a rate, and as long as you interpret 7 o'clock to 9 o'clock as 2 hours, you got a time, and you have a distance traveled. Why am I really putting this problem in front of you? Well, really, it's because I want to consider with you how to approach this same problem using a physics velocity graph. Oh, okay, getting a little fancier now. Now again, if you haven't taken physics, it's okay. You can completely understand the math behind this, but we need a velocity graph. Now, a velocity graph doesn't have to be something real scary. Honestly, it just means that we're going to be graphing time on the x-axis and velocity on the y-axis. And the velocity that we're going to be graphing is the 75. Now, when you graph a velocity to 75, you honestly just draw a line, you draw a graph that is up at 75. Now, I think we have some times to also think about here, right? We have a 7 o'clock to like 9 o'clock. Now, remember, this is the same problem, so it should have the same answer. I wonder how 150 can be derived from this graph. How about the area of this graph? Remember, we said a couple slides ago that this half of the year will have something to do with the area. I'd like you to consider with me for a moment making a space on the velocity graph, or you might say under the velocity graph, between 7 and 9 o'clock. Now, the space that I just made here, it has an area. It certainly has an area that is denoted very simply by the dimensions of this space, right? The dimensions of this space, it's not a trick question, are definitely 2 and 75. And if I know the dimensions of this space, I'm pretty sure I can get the area of this space, and, well, would you look at that? The area ends up to be the distance traveled. That may be something that you want to make note of, that the area of this velocity graph, or maybe more specifically the area under this velocity graph, is equal to distance, or distance traveled. Now, what we're trying to do here is honestly just make a simple connection. and that is that if you take time and you multiply it by speed or rate, so if you take a rate and you multiply it by time, you get a distance. And that same multiplication is what's happening when you calculate the area, the two-dimensional area under this graph. But what if the velocity varied? What if it was honestly a little bit more realistic? What if my velocity graph wasn't just a box? Maybe the train sped up. Maybe the train slowed down. Is there still an area? Is there still an area? Well, 100% yes, there's still an area. It can be helpful to use the same times, but what you kind of notice here, I want you to notice, is that when you have boundaries, that is like x boundaries, or in this case t boundaries, those boundaries can then correlate and create a space, a two-dimensional space. And if you think about it, all two-dimensional spaces have area. So how would I find this area? Well, I'm not going to have a number answer, silly, because I don't have an actual equation with numbers. But I can think a little bit about the labels, because the rate is still miles an hour. The rate times the time is going to still be times hours. And so even if my space up here is a varied space, if it's not like a common geometric shape, the simple mathematics of the factor label method of some simple multiplication tells me that my area is still going to be a distance. And that is because the area under a velocity graph is always equal to a distance, or a distance traveled. Now, the point behind this little intro is just for all of us to say, okay, area sounds like something to talk about. Indeed, it is something to talk about. We'll be talking about it for the second half of the year. But, of course, not every day. We won't be just doing area. But ultimately, it does relate back to this. So let's kind of start at the beginning. Let's actually find some areas. And as you're going to learn, let's find those areas by estimating. We're actually going to start with an estimation technique. Don't worry, this is all part of the calculus progression, and you'll be glad that you did this. This isn't just kind of a waste of time. It helps us to get set up very nicely. So this is a good problem to start with, a nice little parabola, y equals x squared. We're going to talk about the area under y equals x squared from x equaling 0 to 6. The area under y equals x squared from 0 to 6. First thing here would be to understand that there is a visual component to this problem. The truth is, just about every problem we do in this chapter 5 is going to have a visual component. And I find out that students kind of like that. They like the visual piece. Perhaps maybe there's some of you that won't like that, but again, most students kind of say, yeah, I like visualizing, and the whole point here is to help you guys realize that it is part of helping you to get your answer. So I have my parabola, y equals x squared, from 0 to 6, and it is, of course you saw the train problem, but this is still kind of a first time look at this. That is for us just to start to see area. You want to see that the area that we're looking for is under the parabola. And notice that it's stopping at the x-axis. Yes, that's kind of a given, if you will. That's how this works. The area is always, the boundary of the area is always the x-axis. Okay, well, we want to estimate this area. Anybody got any ideas? Well, if we were talking about this together, maybe somebody would say, hey, how about a triangle? Yeah, you could kind of think about a triangle here. It seems to have a lot of wasted space, but it's a possibility. How about a rectangle? Could we kind of think about like some rectangles under here? Well, it turns out that that's where we're going to start. We're going to start by using rectangles. But we need some more information. We need some, basically some details about these rectangles. I'm getting ahead of myself here. So first of all, when using rectangles, we're actually using what's called the rectangle approximation method, abbreviated RAM. Now listen, I'm not making this up. This isn't just Mr. Naylor. This is how you do estimation using the rectangle approximation method. So, what I need is to be told how many rectangles. And that'll be described to you in this manner. Let's use 3, often called subintervals, but what that's really referring to would be the 3 rectangles. So, yeah, we're just going to basically try to draw 3 rectangles underneath this space. So that means I need to divide up my space equally, right? I got to divide it up equally. Now there's going to be 3 subintervals, so I hope that each one of them is 2 units from the previous or to the next. So that means I'm going to have a rectangle from 0 to 2, from 2 to 4, and 4 to 6. I've got 3 subintervals. Now, exactly how do I draw these rectangles? Well, you guys are going to learn that there's 3 different ways. And one of the ways is by drawing them to the left, which is actually called the LRAM, which means the left hand rectangle approximation method. Let's start in this last interval. It's usually an easier one to start in. So I'm starting in the interval from 4 to 6. And I'm now going to focus on the left side of this interval. I'm going to, if you will, go to the left. And when I go to the left, I get to the x value of 4. Now, the x value of 4 tells me, or I should say, when I use the x value of 4 to meet the parabola to create my y value, I see that my rectangle is going to be of this orientation. So that rectangle, you might say, is drawn from the left or using the left of my interval. Think you can do it for the next interval? I'm kind of working backwards here. So we're going to go to the left of this interval. We're going to use that x value to generate our y value. And it's not very big, is it? It's only going to sort of be squeezed or tucked into that space. But that rectangle is to the left of that other or that next subinterval. Now the reason I didn't start with this subinterval is because when I go to the left, I get no y value. So I have no rectangle, I have no dimension, no height dimension. Okay? Not a big deal. I still have 3 subintervals drawn here, each of them creating a rectangle, which, as we're going to learn, each have an area. And those areas are simply denoted by the dimensions of these rectangles. That is the y values. Now, these red numbers that I wrote down didn't just come from magic, they came from the equation. So keep in mind that I simply plugged into the equation, and that gave me each of those y values. But really, those y values become part of the dimensions of each of these rectangles. And now I'm going to be able to organize my LRAM, or I should say my three different rectangle areas of my LRAM. This R1, R2, R3 stands for rectangle 1, 2, 3, or region 1, 2, 3. And I'm simply going to multiply the length times the width and generate my area. Of course, the first rectangle has no area. The length of the second rectangle you could say it's the y value of 4. And of course, the width is still 2, so now that rectangle is an area of 8. And what do you think about the last one? Length times width. Now, these 3 rectangles, when added together, give me the approximation of the area, again, using the LRAM. I know what you're thinking. That's not a very good approximation. First of all, it's only really using these 2 blocks right here, which means that it's leaving out quite a bit of space. It's leaving out some of this green space here. So what's the deal? Well, the deal is relax. It's just an approximation. And it actually can be used along with another type of RAM called the right RAM to perhaps generate another approximation. Yeah, the RRAM, the right RAM. Now, not right meaning like right versus wrong, but just the one that's to the right of each one of these subintervals. We're still using 3 subintervals, but we're going to generate this from the right. Now, when you generate this from the right, what you want to do is you want to go to the right side of your interval. Notice that I decided to start really with the first one this time. I go to the right, and that x value, or at that x value, I go up and meet the graph. Of course, when I go up and meet the graph, I am able to see that my rectangle would be this one. Notice it's kind of outside of the area. Okay, that's okay. Let's go to the right of my next region. If I go to the right, I get to the x value of 4. I use the x value of 4 to generate my y value. When I generate that y value, I create my next rectangle. Maybe you want to draw the last one. If you haven't already, you might want to draw the last one. And we get the 3rd rectangle. Now, just like in the other problem, the dimensions of each of these rectangles, the length and the width of each of these rectangles is going to be super important for getting the area. How do you get these dimensions? How do you get the y values? Of course, you're just plugging into the equation. Hey, notice that each of these y values came from the right side of each of these regions. So are some of these y values duplicated from the previous problem? Yeah, but some of them are new. This is called the right RAM. Each of them is still 2 units long, so I can find the area of region 1, or rectangle 1, 2, and 3. Length times width. Length times width. And length times width. This is how you go about a rectangle approximation problem. I know sometimes kids can say it's kind of simple, might even feel a little bit more like geometry, but you're actually doing calculus. You're actually doing calculus as you create, or as you just use this simple area concepts to find, again, an approximate area. Now that approximate area, I don't know what you think. Do you think it's better? That's not the point. It's not to say that it's better or worse. It's just what you would get if your rectangles are drawn from the right or to the right, and you're using 3 of them. It is certainly a very different answer than we got on the previous screen. It's greater. Indeed, there's some weight, there's some extra space that we're accounting for. But there's another way. There's another RAM. We did the left, we did the right. What else could there be? The middle, the MRAM. If you draw your rectangles, in a sense, using the middle of your intervals, this one takes a little bit, being a little bit more careful with your drawing. Okay, what I'm talking about here is that I definitely have an interval. The interval is still from 4 to 6, But now I want to go to the middle of it. When I go to the middle of it, I find an x value. And that x value is going to be used to generate my y value. That is the height of my rectangle. Comes from the middle of my interval. Now, did you see how I drew that? Let's try it again. You go to the middle of your next interval. It's still the full interval, but at the middle, I'm going to go up, touch my graph, and again generate a y value, a height that's going to create a rectangle that's kind of a little bit inside and a little bit outside of the curve. Now, as you've seen in all the previous problems, the y value at each one of these x values is super important. So plug them back into your parabola equation, your y equals x squared equation. And we're ready to duplicate this little process, this little organization one more time. You're going to use the length and the width of each of these rectangles, of each of these regions, to, of course, generate an overall area. And I wonder what kind of answer we're going to get here. How accurate is it going to be? Do you feel good about it? And of course, you just add these up, and you end up with an MRAM of 70. Okay, now you don't have to be that observant to recognize that we found three answers that were altogether very different. We found an LRAM, oops, too many L's. We found an LRAM that was probably too low. We found an RRAM that most likely was too big. And we found an MRAM. Well, be careful. Nobody said that the MRAM is the one that's right. Actually, what you want to realize is that all of these are just approximations. But could I do something with these three approximations to perhaps even hone in on an even better approximation? For sure. We could find the average. And the average of these areas, when, of course, added together and divided by 3, actually comes out to be 74. Now, again, is somebody saying that that's the right answer? No, nobody has said that yet, but perhaps it might be the best answer if I was going to kind of submit what I think is the best approximation for the area from 0 to 6 of y equals x squared parabola. Okay, now, yes, these rectangles, they're still not the best. They're not giving the actual answer. But there is something we could do to at least make this a little bit better. Something that we haven't still done, or we haven't done yet. If you think about the rectangles that we drew, all of them are pretty boxy. Now, that's how rectangles come. They are boxy, but couldn't I make my rectangles like a little less boxy? Like, couldn't they be smaller? Couldn't they be like a little more precise? Sure, they could be. All I would have to do is increase the subintervals. If I increase the subintervals, if I basically use more of them, my rectangles will become a little smaller, a little bit more precise. Now, what I usually encourage kids to do at this point is to actually try this, to see if you can take the simple diagram that we've been using, that is a parabola, from 0 to 6, and see if you can maybe start to draw on your own for the first time what it would mean to use 6 subintervals, 6 rectangles here for the RAM method. If you want to pause the video, you can. In a moment, I'm going to show you the RRAM Yes, let's do the RRAM since, of course, I'm sorry, let's do the LRAM. That's usually the one that we start with. So if you're going to draw these rectangles on your own, which you should, why don't you try to draw them to the left of each interval? So push pause, but if you want to see the next step, well, push play. Now what I did here was just simply divided my interval equally by 6. If you divide an interval that's already 6 by 6, then each interval needs to be 1 unit long. I know, kind of common sense, but you'll be doing that for some harder problems soon. So we just want to divide the interval equally. I tend to start at the end because I don't want to start over here at 0. If I'm going to show you 1, I'm going to start at the end. So what did I do here? I drew my interval. I drew my dimension to the left. I went to the left. I'm using the left x value. And when I use the left x value, I go up and meet the graph. I meet the graph and I create a rectangle. And then we keep doing that. Go to the left. Once you draw one of these, usually it's pretty easy to draw the rest, but these are the ones that are going to the left. Notice that I'm using the x value on the left to find the y value. Of course, that y value is going to have a lot to do with the dimensions of each of these rectangles. Don't be scared to push pause, push play. You should be trying to do this on your own. Don't make the first one you do when it's time for the assignment or the quiz. Those are, of course, the y values that go with each of those x values. Ultimately, those are one of the dimensions. You might call it the length, because the width is just 1. Just kind of getting started with some of the first rectangles. Somebody says, do I have to write all this down? I suppose you don't have to write it all down, especially in a problem like this. Maybe you can already see that since we're just multiplying by 1, that what you're actually going to end up doing is just adding the y values. Well, that's an interesting observation. As you'll learn a little bit later, the concept of an antiderivative, I haven't really talked much about that since the beginning of the lesson. The concept of an antiderivative has a lot to do with adding or summing up numbers. That's exactly what's happening here. We're going to add up 0, 1, 4, 9, 16, and 25. Of course, that's just the addition of those y values. So we call that the LRAM. So when we increase to 6 subintervals, would you agree that the at least the LRAM that we found, it became more accurate? There was definitely less wasted space with those smaller rectangles, and you can even see that the answer that we found it got a little bit better, at least a little bit closer to that average answer that we had found previously. If you compare it, of course, to the original number that we had of 40. Now, again, nobody's saying that 70 is the right answer, but we are saying that it's probably a better answer than 40, and we're noticing that 55, of course, is getting closer to that better answer. But it should, because we have more rectangles. We increased the number of subintervals, which in effect decreased the number of wasted space. Now, tomorrow what we'll do is we'll get out your calculator and we'll use the programs that should have been installed. We'll use those calculator programs to continue to investigate the idea of the RAM, or the rectangle approximation method. Okay? If you don't have those programs, you're going to want to get them. You can come see me, or maybe use a friend's cable to get them transferred to your calculator for tomorrow.